this is an example of a N-type doping where you have silicon surrounded by a phosphorus impurity. Now, 4 atoms of phosphorus are binding with silicon, but the fifth electron of phosphorus cannot bind to anything because there are no empty spaces of binding left here, and so it becomes kind of a free electron. So every phosphorus atom therefore donates a free electron to the material. Similarly, for boron, you have 4 atoms of silicon but only 3 atoms of boron. So there is an empty spot left as a hole in the boron atom's crystalline structure with silicon, which acts as a flow of holes. So hence this is called a p-type semiconductor. And you can see the donator levels of electrons and the acceptor levels of the poles. So you have this kind of a structure. In this case, you have donator levels in the conduction band, close to the conduction band, which are donating electrons to the conduction band, and acceptor levels close to the valence band, which are donating holes to the valence bands. Okay. So this is the p-type and n-type semiconductors. Now we can discuss in detail what is a p-n junction diode is like. You have n-doped semiconductor and a p-doped semiconductor. Think of silicon only. One side has been doped with phosphorus as n-doped, so it has an excess number of electrons, and on the other side you have p-doped with boron, so you have an excess number of holes. Now you make a junction between these two. It is not a simple kind of a junction. Basically, it's a one crystalline structure. Part of it has been doped with boron and part of it has been doped with phosphorus. Just pasting two things won't work here. Okay, so that's the art of material synthesis of a semiconductor system. So here you have a free holes and here you have a lot of free electrons. So what will happen is the free electrons will diffuse into the holes that are present in the p-doped side and hence create a region of recombination here. These electrons will go and merge with the holes here, or conversely you can think of these holes will go into electrons and merge here. Okay. So what is then happening is, in this recombination zone, this side has less electrons than is required for charge balance, because remember this both n-type and p-type were electrically neutral. Yes, there were free electrons and free holes, but those were not present because you are putting extra electrons from over and above what is required to keep the charge balance. Phosphorus atom is a 5+ atom, okay, and boron atom is a 3+ atom. So the absence of the presence of holes and the presence of extra electrons are basically keeping the charge neutrality. So now when in this region, when these electrons disappear due to recombination and when these holes disappear due to recombination, you get a positively charged zone here where you are its charge depleted, and a negatively charged zone here where you have excess charge because electrons have traveled to this side. Okay, so you get a positively charged zone in the n-doped section and a negatively charged zone in the p-doped section, creating an electrical field that moves from the n-doped to the p-doped section across this junction. And this field exists along what is called the depletion zone, where the free charge carriers, electrons for n-type and holes for the p-type, are absent because they have recombined. So this region is called the space charge region. Okay. We have also noted that so there is a electrical field acting across this space charge region. We have also noted that for n-type regions, the Fermi level moves closer to the conduction band, and for the p-type region, the Fermi level moves closer to the valence band. Okay, we don't have to worry about what these values are here, just that these two levels are moving in opposite sides. Now, when you do this kind of a junction, what interestingly happens is that the Fermi levels on two sides equalize. Okay, so the Fermi level on this side will be equal to the Fermi level on this side. EF n-doped will be equal to the p-doped case. So this level becomes constant. It's like a water level which remains constant. So what happens therefore is that the conduction band level in the n-type go below the conduction band level of the p-type to preserve the distance. This becomes equal to this. So this must go down and this must go up. And this is what you are seeing here. Similarly, this is close to this. So this spacing is preserved. But here, because it's so far away, this has to go down. So the energy levels of the n-type side actually go below the corresponding energy levels of conduction band, valence band of silicon of the p-type side. Remember, this is still silicon material on both sides, right? But there is now a mismatch of the energy levels on either side, and there is a transition on the energy levels as you move from the n side to the p side. Your energy levels for the bottommost energy level of the valence band and the topmost conduction band and the topmost energy level of the valence band rises. Okay. So here is the space charge region. Here is the region where the E is changing as well. Okay. So for the PN junction, the salient features are then this. At the PN junction, the free electrons on the n side migrate and combine with the free holes on the p side. This creates a charge imbalance and hence we get a potential gradient across the PN junction within the free charge depletion zone. Okay. So basically what is happening is, if you think of the PN junction is like this. This is your PN junction. This is your N side. This is your P side. These are your atoms. Sorry. Okay. And you have free holes here and free electrons here, balancing the positive and the negative atomic cores. Okay. But within this zone, there are no free electrons and holes. So you have a positive side charge here and a negative charge here. This is called the depletion zone D, with a positive charge here and a negative charge here, creating a potential gradient E across this zone. Okay. Now this potential gradient E means that there is now, these electrons have to move against this potential gradient to go to these holes, and these holes also will have to move against this potential gradient to get to these electrons. Okay. Remember, in a potential gradient, holes move from positive to negative spontaneously and electrons move from negative to positive spontaneously. Okay. But here you have electrons on this side and holes on this side. So electrons will need to do work in order to move across this potential energy, and similarly holes. So this space, this depletion zone and the corresponding potential gradient is what prevents the further migration of electrons and holes towards each other. So the migration basically stops once this potential gradient develops. So if the electric field is E and thickness of depletion zone is D, then there exists a built-in voltage across the PN junction that prevents the further migration of electrons and holes across the junction. This is given by VBI. V built in equals to the electrical field E into the length of the depletion zone D. Okay. So as we noted, by the equality of the Fermi level across the depletion zone for both zones, so this is the conduction band and this is the valence band and this is the Fermi level. Sorry, it looks kind of a wiggly line. This is basically a straight line here. Okay. Actually, let's redraw this for clarity. This is the Fermi level. Okay. So what you have here is that this is the N side and this is the P side, and in this zone is your depletion zone. Okay. Like this. Okay. So this is where the energy level is actually changing while your Fermi level is remaining the same. Okay. Now, in the N side, you have a lot of free electrons from the phosphorus atoms that are located in the conduction band. So you have lot of free electrons that are near the bottom of your conduction band. Free dopant electrons. Okay. Now these electrons cannot move into the conduction band of the p-type zone because of this potential gradient here. Okay. So this potential gradient this distance between the top of the conduction band in the p-type and the top of the conduction band in the n-type is given by Q into VBI. This is the energy. Okay. This is the energy difference where Q is charge of an electron or hole. Okay. So this is the built-in voltage. So the total energy difference between the two sides is Q into the built-in voltage. Okay. Remember, n-type is positive. So this side is positive and this side is negative. So the E is in this direction. Okay, from the n-type to the p-type. And because of this energy difference, these electrons cannot move here. Alright. Similarly, you have a lot of free holes in the valence band area on the p-type side. So these are the free dopant holes. Okay. And again, because of this energy gradient here, these holes cannot travel on this side. Okay. And that is why further migration of electrons and recombination into holes is being stopped by this energy gradient. You can think of electrons at this side as like pebbles who want to go to the lowest possible energy level, while holes are like bubbles which want to go to the highest possible energy level. Okay, so these bubbles cannot go down and the electrons cannot come up because of this gradient. Okay, so now is the most important aspect. We have looked at the p-n junction and now we will see what happens when sunlight is incident on this p-n junction. So let's see an illuminated p-n junction. Okay. So here, let us redraw this system once more. I will try to be a bit more careful this time. This is your junction. Okay. This is your N side. This is your P side. Okay. The Fermi level, as we discussed, is this one. Okay. And you have your electrons here, and you have your holes here. Now suppose you have sunlight coming and illuminating this p-n junction. So sunlight is falling on this p-n junction, okay, from the sun. Okay. Now the valence band has a lot of electrons. Okay. What will happen is some of these electrons will absorb the photons coming from the sunlight and hence get promoted, will have enough energy to jump from the valence band to the conduction band. So this is very important. Unlike thermal energy, solar energy photons also have sufficient energy for the electrons to go up from the conduction band to the valence band. Okay. So what will happen is that an electron here will absorb a photon and will jump to the conduction band here, and instead of an electron here you will get a hole. Okay. So this promotion will leave a hole in the valence band and an electron in the conduction band. So you will get a series of holes that are being generated here and a corresponding series of electrons that are being created at the bottom of your valence band or conduction band. Okay. Now you see these electrons are on this gradient. So they will go down to the lowermost energy gradients and move towards the N junction. While these holes always try to rise to the topmost available energy level. So these will move towards the P side. Okay. Now this is a positive charge moving this way and negative charge moving this way. So the overall effect will be a current will start flowing. So you will get a current that will flow in this side, which is called the light current. Okay. So the illumination of a PN junction with sunlight will produce a current that will flow from the N side to the P side through the PN junction diode. Okay. So now once this happens, you will get a flux of electrons flowing this way and a flux of holes flowing this way, and you will get a overall electrical current flowing from the N side to the P side. And now if you so suppose this is your material. Okay, this is your total solar cell material. Okay, and you are connecting this material with an external circuit which has a resistor, say a light bulb. Okay, then this light current will flow this way. You can think of it as a flow of electrons this side. Okay, will flow through this side and will move this way. Or you can think of it as electrons flowing this way, going to this side, go up to this side and recombining with the holes here. Okay, and thus as soon as you have a external circuit, you will get a flow of electricity going from the P side to the N side, so the external circuit, and a flow of electricity going from N side to the P side in the internal, to the interior of your solar cell. So this is your basic structure, and this is how you are generating electric current in your solar cell. Okay. So we will stop here. Just look at this carefully. This kind of neatly explains the physics, how the energy of the photon is being absorbed by the electrons in the valence band of your doped silicon conductor across the PN junction, creating electrons in the conduction band and holes in the valence band. How these electrons are flowing across the potential gradient towards the N side, holes are flowing across the potential gradient towards the P side, and then the electrons are flowing out through the external circuit and recombining with the holes at the opposite end of the P side, creating a light current in the opposite direction. And this is the direct conversion of the sunlight, the energy of electromagnetic waves in h nu of the photons, into a flow of charge through a resistor which is generating work. Okay. So we will start from this basic physical understanding and flesh it out with more quantitative understanding in the next class. Thank you for listening, and we will meet you in the next class. Thank you.